Welcome students. I am Dr. Monika Khetarpal. I am Associate Professor of Physics in Government Dungar College, Bikaner. In my lecture series of MSc Previous Physics, I was dealing with the paper First Classical Mechanics. In that, we have derived canonical equation of motion. The canonical equation of motion are Qj dot equal to del H upon del Pj and Pj dot equal to minus del H upon del Qj. Here, H is the Hamiltonian of the system. This Hamiltonian of the system depends on Qj, Pj and T. Qj is the generalized coordinate. Pj generalized momenta. T is the time. Depending on the number of generalized coordinates, there will be, suppose if there are n number of generalized coordinate, then there will be n such equations, and similarly there will be n such equations. So there will be 2n canonical equation of motion. These canonical equation of motion are of first order. Now we will derive these canonical equation using variational principle. We have already discussed Hamilton variational principle. I am going to give you a brief. What is this principle? Hamilton principle is integral Lagrangian dt from time t1 to t2. This must be equal to extremum. This integral must be extremum. Or we can say that variation of I, it must be equal to 0. Here L is the Lagrangian of the system. It is a function of Qj, Qj dot and T. This is the Hamilton's principle. Now what we are going to do, as we have to derive canonical equation of motion. And the canonical equation of motion, they are in terms of Hamiltonian. So we will change this variational principle from L to H. The relation between H and L is Hamiltonian being summation Pj Qj dot minus L, or L equal to summation Pj Qj dot minus H. So in this Hamilton principle, I am substituting L to be summation Pj Qj dot minus H. Therefore, del I equal to del. Instead of L, I am substituting this value of L, Pj Qj dot minus H. This equal to 0. This expression in which we have changed L in terms of H is termed as modified Hamilton's principle. Now, what is this variation? This variation is d alpha del by del alpha. What does this alpha stands for? Suppose we have one initial point, and from this initial point we have to move to another final point. We can follow many paths from one point to another. We have labeled these different paths by indices alpha. And this variation has been expressed in terms of alpha. So modified Hamilton principle, by substituting del to be d alpha del by del alpha, comes out to be this. Now, since del by del alpha, this factor is independent of time, it can be taken inside the integral. So I am taking it inside the integral. D alpha is outside. differentiating the first term with respect to alpha, I will get two terms. And from this Hamiltonian, I will get in terms of partial, because H depend on three terms, we will get these three terms. Now, in the last term, we have del t by del alpha. What does it mean? That there is a variation of time with respect to path. But we know that in moving from initial point to the final point, time of travel along every path is same. So del t by del alpha, this is equal to 0. So we have substituting in the last term to be 0. Now this second term is integral pj del qj dot del by del alpha. What does qj dot means? Qj dot is dqj by dt. This is dqj by dt. We can interchange the differentials. I am interchanging the differential, and then I will solve this integral by parts. First term as it is. What is the first term? pj. Integral of the second term. This term integral will give me del qj by del alpha. Limit is initial time t1 to final time t2 minus integral differential of the first term pj dot. Inside there will be also an integral of the second term, and the integral of the second term gives me del qj by del alpha. Now this first term, variation of qj with respect to path at limit t1 and t2. Since we know that initial and final point, that means end point, are same for all paths, so this variation will be 0. So instead of second term, I am putting minus pj dot del qj by del alpha dt. And recollecting these all terms, first term being the same, we have find the value of second term, third and fourth being same, and fifth term is 0 because del t by del alpha is 0. So I am left with this expression. Now I am taking d alpha inside. Since and collecting the terms of del pj by del alpha. I have two terms. First term is qj dot and the another term is minus del h by del pj. And from these two terms, I am taking del qj by del alpha common. This comes out to be minus pj dot minus del h by del qj. Now, since we know that this function d alpha del by del alpha, this is equal to variation del. So I have substituted this to be del, and instead of this I have substituted del. So I have now two terms. One is the variation term which contains del pj. The second term contains del qj. And we know that in Hamiltonian, pj and qj are independent. So the variation del pj and del qj will also be independent. Now for this integral to be equal to 0, the coefficient must separately vanish. So substituting the coefficient of del pj to be 0, I get qj dot equal to del h by del pj, and from this term I get pj dot equal to minus del h by del qj. Now these two equations, they are known as Hamilton canonical equation of motion. If there are n generalized coordinate, there will be 2n canonical equation of motion. So using variational principle, we have derived canonical equations of motion. Now, I am going to discuss an example of this canonical equation of motion. What we have to do, we have to write the Hamiltonian and find the canonical equation of motion in central force field. This problem of central force, it can be easily solved in r theta coordinates. So, in order to solve this expression, first of all, we are finding Lagrangian. We know that Lagrangian is T minus V. The kinetic energy in terms of r theta, half m r dot square plus r square theta dot square minus V, which is a function of r. This is my Lagrangian. Now, I'm going to derive my generalized momenta. As there are two generalized coordinates, r and theta. So we will find generalized momenta for these coordinates. What is PR? Del L by del R dot. Differentiating Lagrangian with respect to R dot, I get MR dot. And P theta, this is del L by del theta dot. This comes out to be MR square theta naught. So H, which is equal to summation Pj Qj dot minus L, substituting the values, since there is a summation, I have PR R dot plus P theta theta naught. There are two generalized coordinates. So I am taking here two terms minus L. Putting the value of PR and P theta and Lagrangian and solving the expression, I get half m r dot square plus r square theta dot square plus VR. What is this term? Kinetic energy. So I get H to be equal to T plus V. That means Hamiltonian is equal to total energy of the system. Now, in order to solve the canonical equation, I am going to change these r dot and theta dot in terms of momenta. So from here, I can get r dot to be equal to PR by m and theta dot as P theta by mr square. So substituting the value of r dot and theta dot in terms of PR and P theta, I get Hamiltonian expressed by this equation. Now, I have to solve the Hamiltonian equation of motion. First of all, I am taking my generalized coordinate as theta. As there are two coordinates, r and theta, initially I am solving for theta. For theta, theta dot equal to del h by del p theta. Differentiating Hamiltonian, I get it p theta upon mr square. Another expression is p theta dot equal to minus del h upon del theta. As we can see, there is no term containing theta. So p theta not equal to 0. Hence p theta comes out to be constant. That means angular momentum is, linear momentum is constant. Now, since r is another generalized coordinate, we can solve the expression for r also. R not equal to del h by del PR and PR dot equal to minus del h by del r. So we can solve our problem using canonical equations of motion. The two canonical equations of motion are Qj dot equal to del h by del Pj and Pj dot equal to minus del h by delta Qj. Thank you, students, for watching.